I want to do a practice problem about one of the corollaries for the mean value theorem. So I'm looking at section 4.2, problem 59. So what the actual question says is to graph this function, which as you can see is kind of a nasty function. So we're supposed to be graphing sine of x times sine of x plus 2 minus sine squared x plus 1. When I threw that into Desmos, thank you Desmos, the graph comes out as a straight line. Now, that seems totally weird since we've got all kinds of trig function stuff here, so we're expecting some kind of oscillation, and for the graph to just be a straight line means something interesting is going on. Now, because we've been studying the mean value theorem, we're going to look at this and be thinking to ourselves, hey, if we think about this as one function minus some other function, then corollary 2 says if the derivative of f of x, I'll just call this f, if the derivative of f of x and g of x are the same, then they should differ by a constant, which is essentially what our graph says here. So let's take a look at those derivatives and see if that might explain what's happening. So I'm going to think about this as, first of all, we'll let f of x be equal to sine of x times sine of x plus 2. So if I go to take the derivative, I'm going to have to use a product rule. So I will be quick about that and say f prime of x, derivative of sine is cosine, and then we'll leave the other piece alone. And we're going to add that to leave the sine x alone times the derivative of sine, this time is also cosine. Remember, calculus never changes what is inside the parentheses. So there's our derivative if we look at the first part, the sine x times sine of x plus 2. Now, let's take a look at the second part. So if I come down here and let g of x be equal to sine of x plus 1 whole thing squared. So when I take g prime, this time I'm using chain rule so that 2 comes down from the exponent, and that'll be times sine of x plus 1. Again, calculus never changes what's inside of a trig function. And then chain rule says we're going to multiply by the derivative of that. So cosine of x plus 1. Now, on first look, these two derivatives don't really look anything alike. So now we're going to dig deep into our toolkit and start thinking about trig identities. So up here, I have two pieces that have both a sine and cosine. So the trig identity that I'm thinking about will employ some cleverness is sine A plus B. Now sine A plus B is equal to sine A cosine B plus sine B cosine A. So if that's the case, and we take a look at the function that we've got up here, if we treat A like it's x plus 2, and we treat B like it's x, then this should match up. So coming back in and taking a second look at that derivative, but using the trig identity, I am saying this whole mess turns into sine of what our A was, x plus 2, plus our B, which is x, or sine of 2x plus 2. Oops. So now let's take a look at this guy down here and see if we can't find some other cleverness. So the cleverness I'm thinking of this time, the trig identity that I know with a 2 out in front and a sine and a cosine looks like sine of 2a is equal to 2 sine a cosine a. And this one's actually, I think, a little bit easier to spot. But if we apply that trig identity to our derivative, now our g prime of x is going to turn into sine of 2 times x plus 1, and distributing that out, I'm looking at sine of 2x plus 2. So with the help of a little bit of trig, it turns out that our guess was right, and the derivatives of these two functions are the same, which means by corollary 2 of the mean value theorem, the function f and g must differ by only a constant. So when we subtract them, we would expect to see a graph that's a straight line, a graph that's equal to a constant.